Hello, my name is Daniel. Welcome to this presentation on interference-aware scheduling for inference serving. Let me give you an overview of what we'll be talking about in the next few minutes. First, I'll talk about scheduling and inference serving. I'll introduce some challenges in interference-aware scheduling for inference serving systems and go over some existing methods. Next, I'll go over our proposed machine learning-based scheduling method and show some preliminary results. Finally, I'll introduce some future research directions in interference-aware scheduling for inference-serving systems. So first, let us remind ourselves what an inference-serving system is. So in an inference-serving system, users send inference queries to a managed cluster of worker machines, and those worker machines serve the queries. So what does an inference query look like? An inference query includes some input data, such as an image, and it also specifies an inference model, for example, ResNet, and it may also specify a service level objective, or SLO, such as an inference latency constraint. And so the role of the scheduler in an inference serving system is to place inference models and queries on worker machines. One tool that's commonly used in inference serving systems is collocation. Essentially, what collocation is placing multiple models on the same worker machine. The reason why we do this is that it improves hardware utilization and in turn reduces cost. However, the downside to collocation is that there's a possibility that the collocated models interfere with one another through resource contention. This can cause inference latency degradation. And we've observed that when collocating models, the inference latency can slow down by up to 1.8x. This means that these models are susceptible to SLO violations. So what we need in an inference serving system is an interference-aware scheduler which can minimize the collocation latency degradation and avoid SLO violations. Let's start talking about some of the challenges in developing an interference-aware scheduler in an inference serving system. So first, there's a large number of collocation configurations. In fact, there's an exponential number of collocation configurations according to the number of inference models. And each collocation configuration requires about 1 to 10 seconds to profile. So this means that profiling all collocation configurations is intractable. Another challenge in developing an interference-aware scheduler is that the slowdown varies across collocated models and across machine types. To show this, what I'm showing here is the plot of DenseNet 201 slowdown when it's collocating with a bunch of different models on a 24-core CPU. So in this plot here, the vertical axis is the slowdown of DenseNet 201, and the horizontal axis are the models that DenseNet 201 is collocating with. What you'll notice on this plot is that the slowdown actually depends a lot on what model is collocated with DenseNet 201. Next, now on the right, I'm showing the slowdown of DenseNet 201 when it's collocating with a bunch of different models on an NVIDIA V100 GPU. So what you'll notice from comparing the CPU data on the left and the GPU data on the right is that when we're collocating the same pair of models on the CPU, the slowdown can actually be quite different when collocating on a GPU. So what this shows is that there's a variance of collocation latency degradation across collocated models as well as machine types. And this exemplifies the difficulty of predicting the effects of collocation on latency. Another challenge in developing an interference-aware scheduler for an inference-serving system is that through the inference execution of these inference models, hardware utilization can actually vary quite a bit. So for instance, I'm showing the utilization over time of DenseNet 201 on the left and VGG16 on the right. Both models in this case are running in isolation on a 16-core CPU. And what you'll notice by observing these plots is that the utilization over time actually varies quite a bit. And so the highlight here is that variations in hardware utilization exacerbate the difficulty of anticipating how collocation affects the inference latency. Now that we've seen some of the challenges in interference-aware scheduling for inference-serving systems, let's start talking about some prior work in inference-serving systems. So there have been many work that has been done in inference serving systems. These systems on a high level target things such as ease of use and automatic resource management. However, we note that the previously proposed techniques are interference unaware in that they make no attempt to anticipate the effects of collocation on latency. Next, let's talk about the prior work that's been done in interference-aware scheduling. Interference-aware scheduling is a well-studied subject. However, we note that these approaches that have been previously proposed were really designed for homogeneous systems or were designed for workloads that are static and long-running. We note that these frameworks that have been previously proposed are not suitable for inference-serving systems because inference-serving systems are highly dynamic and are not necessarily long-running. For instance, the inference execution typically only sustains for a few milliseconds. So in this work, we propose an interference-aware scheduler that's suited for inference-serving workloads. Specifically, we propose developing a predictor for collocation latency degradation and then developing a scheduler that leverages this predictor to place models that minimizes the predicted latency degradation. To develop the collocation latency degradation predictor, we propose employing machine learning methods to obtain a mapping between the characteristics of inference models and latency degradation. So let's go over how we go about predicting latency degradation. One naive approach is to use separate predictors for each machine type. The problem with this approach is that we cannot exploit similarity across machine types. For instance, the collocation behavior across an 8-core CPU may be similar to the collocation behavior on a 16-core CPU. So in our work, we suggest using a unified predictor across all collocation configurations. In this way, the unified predictor can exploit similarity across all collocation configurations, thus improving data efficiency over the separate approach. Here I'm showing an abstract illustration of the unified predictor. The unified predictor inputs some inference model metrics. For instance, we use the hardware profile metrics of the models, such as the hardware utilization and memory usage. We also include a machine type encoding. This machine type encoding indicates to the unified predictor which machine type to predict the collocation latency degradation for. This machine type encoding can be learned to best exhibit similarity across collocation configurations. Experimental results showed that we get up to a 32% decrease in mean absolute error from using the unified approach against the separate approach. If you would like to know more about the specific scheduler mechanisms, please see the paper. But for now, let me briefly go over some of the preliminary results. So here what I'm showing is the cumulative latency degradation in seconds from 100 random inference workloads using different scheduler policies. Here we're showing the results first of a baseline least loaded scheduler, the proposed interference-aware scheduler, and an auricular minimum scheduler. The auricular scheduler is a scheduler that can perfectly predict the latency degradation due to collocation and exhibits the minimum possible cumulative latency degradation for the workload. The takeaway of this table is that the proposed interference-aware approach performs similarly to the auricular scheduler. Further, the proposed approach exhibits latency degradation more than 2 times lower than the least loaded scheduler. Now let's talk about some future work and research directions in interference-aware scheduling for inference serving systems. First, one path for exploration is the use of active learning for predictor training. So in this study, we use random sampling to collect the training data for the collocation latency degradation predictor. However, we may improve upon random sampling by using active sampling to improve the data efficiency. Here, what I'm showing is a plot of the results of randomly sampling data against an observed minimum. What this data suggests is that there's a sampling approach which does better than random. To briefly list a few more potential research directions, another path is to investigate how to develop collocation prediction for power consumption. Essentially, instead of developing predictors for latency degradation, we develop predictors for power consumption. Then we may develop a scheduler that can optimize for power consumption. Next, we can also look into using clear box architectural features for predicting collocation latency. In this study, the features that we used were hardware profile metrics such as memory usage and hardware utilization. Finally, another direction is using reinforcement learning for interference-aware scheduling. To summarize this presentation, we discussed challenges of interference-aware scheduling and inference serving that made it difficult to anticipate the effects of collocation on latency. We then introduced a proposed machine learning-based interference-aware scheduler and showed in some preliminary results that the scheduler exhibited latency degradation more than 2 times lower than the least loaded scheduler. We also demonstrated that the machine learning-based approach performs close to an auricular scheduler. Finally, we introduced some future work and research directions in interference-aware scheduling in inference serving systems. If you have any questions, please email the email shown at the bottom of this slide. Thank you.